For our third podcast on kinetics, our vocabulary will be dealing with first order, zero order, second order reactions, and half-life. You want to make sure that you're understanding the idea that reaction rates that depend on temperature and other environmental factors are determined by the changes in concentration of the reactants or products over time. So you should be able to analyze a concentration versus time graph and determine what kind of a order it is using the integrated rate law. Okay, so is it zero order, first order, or second order? Okay, and then you should also be able to connect half-life of a reaction to the rate constant, that's K, for first order, and justify the use of this relation in terms of the reaction being first order, which means it's not going to depend on the concentration. Okay, so these are your learning goals and the concepts behind Big Idea 4. Okay, for our third podcast, we're going to focus on the integrated rate law, okay, and we'll be looking at each case individually. That means first we'll look at first order, then we'll look at second order, and then we'll go back and look at zero order, and all of it in terms of the integrated rate law. So as you can see here, we're dealing with first order, okay? Here is the differential rate law, and then when you use calculus and use integration, you change this into this form. So this is the integrated rate law form of this. Okay, so notice that it deals with natural log. Okay, also notice that it's written in the y equals mx plus b form. That's your point slope form, which means we're going to be dealing with graphing and data. Okay, so here's all the symbols for all of the letters up above. Again, the concentration of the reactant at whatever time we're dealing with. This is the initial concentration, okay, and this is the rate constant. Notice the negative for a negative slope. Okay, now if you look in your textbook on page 564, there's some important things to note there. It's a purple box, or mauve, I don't know what color you call that, at the bottom of the page, and it just gives you some important information about the first order integrated rate law. For example, it tells you that the equation shows how the concentration of A is dependent on time. If you know any of the three variables, you can find the fourth. Let's see, the integrated rate law for first order can also be expressed in terms of the negative KT, okay, so we can move everything to the other side. And so there's important information in the highlighted purple boxes. So remember, you should be reading as you're listening to podcasts and focus in on those purple boxes to help you review. Okay, so we're going to continue on with first order. Okay, and we'll get to the next slide. Okay, there we go. And what we're doing is we're taking from a previous podcast the concentration of that decomposition reaction. And we're going to take the natural log of that information, okay, and so it turned it into, it turned it into this information here. So here's the data from taking the natural log of the concentration data from a previous podcast. And then once you plot that, so you can see it's plotted over here, here's your y, here's your x of your integrated rate law, it forms a straight line. Okay, so if it had not formed a straight line, then we would have known that that decomposition reaction of N2O5 was not first order. But because it formed a straight line, that's how we know. So we use graphing to also be able to determine which order the reaction is working with. Okay, another important concept is half-life. Okay, so half-life is the time it takes for the reaction to get to half of the original concentration. Okay, so to turn half of itself into its product. And so, as you notice here in this formula, that half-life, denoted T1/2, is only dependent on K. There's no concentration information here. Okay, so that means that T is going to be a steady value. It's going to be the same half-life every time. For instance, if the half-life is 2 minutes, then every 2 minutes, half of the original concentration will have changed into product. And so this is a good formula to remember for helping you to calculate K. Okay, so here is a sample problem for you to try and see if you can calculate K using the integrated rate law for first order. Okay, so take a minute, pause the video, and see what you can come up with for K. Okay, here's the answer for K. Got to focus in on those two values, and K equals 7.8 times 10 to the negative 3 per minute. Okay, and so let me solve this for you so you can see how to get that answer if you weren't able to come up with it on your own. All right, here's the answer to that last little quick check question on determining the value of K if the reaction is 35% complete at the end of 55 minutes. Okay, so the thing you have to think about is if it's first order, it's going to have this equation, right? Shoot, I keep doing parentheses and I got to do brackets. Okay, this is our first order integrated mathematical relationship. Okay, remember it was derived from the differential rate law using calculus. Okay, so we're just going to plug in our information. All right, so if the reaction is 35% complete, that means 65% of the reaction is still in its original form. Okay, so we won't use 35, we'll use the 65% of the concentration here. Okay, and that's at the end of 55 minutes, so we're going to use 55 minutes here. And then at our original starting point, we had 100% of the original order, or the original reaction, sorry. So since we're going to take out percents, we'll use 1 here to represent 100%. So we're going to have the natural log of 0.65 equals negative K, because of negative slope, and then times 55 minutes plus natural log of 1, our original starting material, which was 100%. Okay, and now you're just solving for K, and so your K should turn out to be 7.8 times 10 to the negative 3rd per minute. Okay, so that's how you solve that problem. All right, let's move on to second order. Okay, same idea as first order, only second order raised to the second power as a differential rate law. Then when we use calculus on it, we get this new integrated rate law. Notice there's no natural log this time. Instead, it's 1 over the concentrations. And the slope is positive. Okay, and all the letters represent the same things. Okay, so if we take a sample problem from our textbook, so if you'll flip to sample problem or example 12.5, you can see the data for these two graphs. So we're showing how that if you take the data and do the natural log of the data and plot those values, or do 1 over the data, the concentration, and you plot them, the one that gives you the straight line will be the order that the reaction is. And so we can see that natural log, which is first order, is not a straight line. So that reaction of C4H6 turning into C8H12 is not first order. Instead, it's second order, because second order is the one that gives you the straight line. Notice it's a positive slope. Okay, so that's the purpose of using the integrated rate laws, is for graphing to determine which order you have. All right, second order also has a half-life, but this time the half-life depends on the concentration, which means the time is not going to be the same value. So as the reaction progresses, concentrations are decreasing, so the half-life is going to get longer. And the way you can tell it's second order is the half-life will double the preceding half-life. So let's say the first half-life was 10 minutes, then the second half-life would be 20 minutes, and so on. It would double it. The next half-life would be 40 minutes, and so on. And so here's a sample exercise for you to try and see if you can determine or write the rate law, and then calculate K, and then calculate the concentration at some time down the road, and specifically that concentration is 525 minutes. Okay, so pause the video, give it a try, see if you can come up with it. Here's the solutions. Okay, and then I'll insert a clip showing how to solve all of those if you weren't able to come up with those answers. Okay, here's the solution for the previous exercise. Okay, here's the problem. The information given, there's the reaction, there's the initial concentration. 2 half-lives have passed, 25 minutes and 50 minutes respectively. What's the rate law? Well, we can tell because the half-life time frame changed, it exactly doubled, we know that this is second order. So the rate law for this is a concentration second order because of this right here. Okay, then the next question was calculate K. All right, so we know it's second order. Okay, we're dealing with half-life, so we need the second order half-life formula, which is T equals 1/2. I got to think for a minute. We're dealing with second order, and it's 1/K times the original concentration. First order does not depend on concentration, but second order does. Okay, so we're just going to plug in our values. Okay, so 25 and original concentration of 5. So we've got, I'll just keep going here. So we've got 25 minutes equals 1/K times 5.0 molar. Okay, we're trying to solve for K, right? So what do we have now? 25 times 5 equals 1/K. Okay, so what does K equal? K equals 1/25 times 5. And so when we take 1 divided by this value, we end up with 8.0 times 10 to the negative third. And then because it's second order, that's going to be our units, so that one of the molarities cancels out. So remember, we always want our rate to be molarity per second. All right, so that was B, calculating K, and then C says calculate A at time 525. Okay, so calculate concentration of A at t equals 525. Okay, so now I have to recall my integrated rate law for second order. And I know it goes 1 over a equals k, let's see, is k negative or positive? Let's see, I think k is positive, just had a brain fart, and then times t plus 1 over original concentration. Now we just plug in our values. So 8.0 times 10 to the negative third at 525 minutes plus 1 over 5. Now you can see I've left out units because we're dealing with concentration. And so I get my values here. So this is 1 over A equals, let's see, I believe that is 4.4 when you add them all together. We want just A, so our final answer should be approximately that concentration. Okay, and that's how you solve that exercise. All right, and our last integrated rate law is zero order. And zero order differential rate law, doesn't matter what the concentration is, anything raised to the 0 power is 1, there's no effect. So you can double the concentration, you can have it, triple it, quadruple it, it is not going to change the rate of the reaction. Okay, and the integrated form of this rate law looks like this. Again, it's just straight concentration there. Okay, again, back to a negative slope. All right, and so what would a graph look like if you plotted concentration versus time? Well, that represents zero order, and if you get a straight line graphing concentration versus time, then you know you have a zero order reaction. All right, zero order also has a half-life formula, and so again, all the same letters there, but notice what happens. We double K, and the half-life gets shorter as the reaction progresses and the concentration decreases. So that's how you're able to tell which half-lives you have. Is first order doesn't depend on concentration at all. Second order, your half-life gets longer. Zero order, your half-life gets shorter. Okay, so here's a concept check for you to stop and kind of ask yourself, how do I tell the difference among zero, first, and second order rate laws from their graphs? Okay, so pause it, think about it a minute. Okay, and the way you'd tell zero order is you would graph concentration versus time to get a straight line, and the slope would be negative. First order, you would graph natural log of concentration versus time if you get a straight line, and again, your slope would be negative. And second order, it's similar to the first order, but you'd have a greater slope, and the slope would be positive, and you're graphing 1 over concentration versus time. Okay, and again, a review of that half-life idea. Half-lives depend on concentration in zero order and second order, but not first order. Okay.
Let's explore the differences between the graphical behavior of different reaction orders. In a zero-order reaction, the concentration decreases in a straight-line fashion as time progresses. The rate constant, K, can be determined from the slope of the line. In a first-order reaction, the concentration does not decrease in a straight-line fashion as time progresses. The graph of concentration versus time is a curve. If the concentration data is graphed as the natural log of the concentration versus time, the result is a straight line. The rate constant, K, can be determined from the slope of the line. In a second-order reaction, the concentration does not decrease in a straight line fashion as time progresses. The graph of concentration versus time is a curve. For a second-order reaction, the graph of the natural log of concentration versus time will also be a curve. If the concentration data is graphed as the reciprocal of the concentration versus time, the result is a straight line. The rate constant, K, can be determined from the slope of the line.
Okay, so a quick review there of rate law orders in terms of graphing. Okay, now this is an excellent summary. I would encourage you to print this slide because it has everything you need in terms of the rate law, the integrated rate law, the slope, whether it's positive or negative, the graphing y and x, and the half-life. So it's everything you need right there summarized in front of you. It's perfect to have in your notes. Okay, and lastly here is an exercise to try and see if you can calculate the concentration of A after 30 seconds, given an initial concentration and a K value for each order, 0, first, and second order. Okay, so pause the video, try it yourself, see if you come up with these solutions. Okay, and then I'll insert a camera clip of the solutions so that in case you weren't able to get those solutions, you know how to do that. Here's the solution for the previous exercise. This was the reaction. This was the original concentration. Okay, this was K. No units put here because we're going to assume the units are appropriate for each order. Okay, after time 30 seconds, what was the concentration of A? Okay, so we're going to start out solving for 0 order. So you have to remember the integrated rate law. So let's see how that goes. Concentration of A equals KT, KT plus original. Okay, now we pop in our information. So we have negative 1.0 times 10 to the negative second times 30 seconds plus 5. Punch that out. Calculator should say 4.7 molar. Okay, now let's go on to first order. So you have to remember first order formula. That deals with natural log. So we've got B first order. Okay, so that's natural log of A, KT, plus 1 over, no, not 1 over, sorry, getting into the second order already, natural log of original concentration. Okay, again, popping our numbers in. So we got 1.0 times 10 to the negative second times 30 seconds plus natural log of 5. And that's going to give you natural log of A. And so then you have to just get A. So you have to do the inverse of natural log. And that's going to give you 3.7 molar. Okay, and then lastly, second order is 1 over A equals positive KT plus 1 over original A. All right, so again, popping in our numbers. And this is what you should come up with. So there's your solutions for solving that previous exercise. All right, and so this is the end of our third podcast. And so in this podcast, you should have learned how to work with the integrated rate law for each order, okay? Relate it to the idea that graphing of the specific integrated rate law, y versus x, giving you a straight line helps you to determine the rate order, and you should have been able to work with the half-life formulas. Okay, so that ends this video.